Hello guys, let's go through the SAT 201. I want to do this quickly so that we don't have to to look at it again tomorrow in class. So let's just see. This test was covering 3 areas of the course that we've looked at so far. The first area, of course, being measurements and uncertainties, basically physical measurement. The second part was, of course, mechanics, and the third part was thermal physics, right? So here was the first question. Students, so this is section A, which was a multiple choice question. So this is the first one. A student measures the length and the width of a rectangular tabletop. What is the absolute uncertainty of the perimeter of the tabletop? So you're given the length there and you're given the width. We are looking for the perimeter, which means we are adding sides, and we know that when we add measurements, the absolute uncertainties, when we say absolute uncertainties, we are referring to these numbers here. The 0.1 is the absolute uncertainty for length, and 0.2 is the absolute uncertainty for width. So if we are going to find the absolute uncertainty in the perimeter, then what we need to do is to add the absolute uncertainties, okay? So these were the options: 0.3, 0.6, 1.2, and 2.4. The answer to this question would be 0.1 plus 0.1, so that means on the length one side and what the other side, so 0.2 plus 0.2 for width and 0.2 for the other side of the width. So we expect the answer to be 0.6. Okay. Right, and the important thing here to remember is that when measurements are added, so we are adding length and width and so on, then the absolute uncertainties will add up. Remember, these are referred to as the absolute uncertainties, okay? The other thing you want to know is that if instead we were looking for the area, in that case, the measurements would be multiplied, so it would be length times width. When we multiply measurements, the fractional or percentage uncertainties are what adds up. So in this case, if we were looking for the area, then the fractional uncertainty delta A over A would be given by delta L over L plus delta W over W. So when we are multiplying quantities, the fractional uncertainties will add up. All right, here is question number 2. A list of 4 physical quantities is acceleration, energy, mass, temperature. How many scalar quantities are in this list? And if you check carefully, you should notice that the first quantity there is acceleration, is a vector quantity. Energy, work done, and that is a scalar quantity. Mass is a scalar quantity, and temperature is a scalar quantity. And therefore, how many of them are scalar quantities? The answer is 3. Energy, mass, and temperature are scalar quantities. Acceleration is a vector quantity. Question 3. A student models the relationship between the pressure, P, of a gas and its temperature, and it's given by that formula there. The unit of P is the Pascal. The unit of T is the Kelvin. That's the absolute temperature scale. What are the fundamental SI units of X and Y? So you can only add quantities of the same type. So if P is X plus YT, then X must be the same unit as P, and YT as it is. That product must also be pressure. So the unit of P are pascals and the unit of T are Kelvin. What are the fundamental SI units of X and Y? So obviously, and we are talking here of fundamental units, so that means if it is Pascal, we have to reduce it back to the base units. And here we can say, so the unit of X here has to be the same as the unit of pressure, which is the Pascal. The Pascal pressure is given by, I'll write somewhere here, pressure is force over area. The force is Newton, so force is mass times acceleration divided by area. This is equivalent to kilogram, acceleration is meter per second squared, and area is meter squared. So one of the meter cancels that, and our result is going to be kilogram per meter, because this goes with one of those, so m is still at the bottom, and this is per second squared. So that is the unit of x, which, as you can see there, these two both satisfy. So the answer has to be either A or B, but we still need to get hold of what y is. Now in the case of y, we know that y times t is also Pascal. So y times t, where t is in Kelvin, all this must be equal to the Pascal. So this must be Pascal. So the unit of y has to be Pascal divided by the unit of t, which is the Kelvin. So here we will write this is the same as, this has to be the same as, the Pascal is what we wrote up here, so kilogram per meter per second squared divided by Kelvin. So this has to be kilogram per meter per Kelvin per second squared. And if we look up there, the answer that matches that would have to be A here, I think. So kilogram there, we have a kilogram there, we have a per meter here, there, we have per second squared there, and we have per Kelvin, and therefore the answer to this question has to be A. Yeah. Let's look at the next question. We'll try to move a bit faster on this section A, except if a question is really challenging, like this one could have been challenging for some of you. All right, so the next question then. A student measures the radius r of a circular plate to determine its area. The absolute uncertainty in r is delta r. What is the fractional uncertainty in the area of the plate? Well, in order to answer this question, we have to write area as a function of radius, and we know that area equals pi times r squared. Now, the constant does not take part in determining uncertainties, so the fractional uncertainty in the area would be written as delta A over A. It must be, we are multiplying r, and we said if we are multiplying quantities or measurements, we add the absolute uncertainty. So this is the same as r times r, ignoring the constant. So because we are multiplying this, we add the uncertainty, it is delta r over r plus delta r over r. In this case, we normally just write 2 delta r over r. So the fractional uncertainty in the area has to be twice delta r over r. Okay. What other information is there? I think that's basically it. A fractional uncertainty in the area would have to be, here is the first answer is A there. There is an option of B, option C, and option D. And from this calculation we've done here, the correct answer has to be A. Right? Okay. All this is related to topic 1. Next question 5. A car takes 20 minutes to climb a hill at a constant speed. That's important. I would underline constant speed here. The mass of the car is 1200 kilogram, and we've said as you go, you want to, so we are saying we want to underline that. Constant speed. The mass of the car is given to us, so mass of the car is 1200 kilogram. And the car gains gravitational potential energy at a rate. So when we see this word here, rate, we are thinking power. So the power, which is energy over time, is 6.0 kilowatts, which means 6,000 watts as the SI unit. Taking acceleration due to gravity as 10, so G is 10 meters per second squared, or if you like, newtons per kilogram. Taking that to be the case, what is the height of the hill? Okay, all right, so what solutions do we have there? We have an answer of 0.6, 10 meters, 600 meters, and 6,000 meters. So what must be the height of that hill if this car is going to climb it? Then we must reason the car takes 20 minutes to do it. So the time taken to do this is 20 minutes. The SI unit for this would be 20 times 60, which is 1200 seconds. All right. And so the energy being supplied, we will assume this energy is becoming the potential energy of the car when it gets up there. So energy must be mgh, because we are looking for the height. Energy itself is power multiplied by time, so this must be power, energy being given per second, multiplied by the total time in seconds for the car. And so we can say H must be equal to power times time divided by m times g. And this is our power, which is 6,000, multiplied by the time, which is 1200, everything divided by the mass of the car, which is 1200, multiplied by g, which is 10. 1200 and 1200 can cancel. 1 there, 1 0 goes with 1 0. We are left with 600, and that must be the height of the car, the maximum height reached by the car. So we expect that answer there to be C. Okay, go to the next question. Most of these questions require practice, because it's not easy to remember things like power times time being energy and relate to potential energy and so on. So you need to know when to relate to potential energy, when to relate to kinetic energy, which particular formula applies at what time and in what instance. Right, let's look at the next question there. Question 6, an electron has a linear momentum of 4.0 times 10 power minus 25 kilograms per meter, a kilogram meter per second. What is the order of magnitude of the kinetic energy of the electron? So the options are, by the way, you can pause and try it out. The options are 10 power minus 50, 10 power minus 34, 10 power minus 19, and 10 power 6 joules. So what's the order of the kinetic energy of this electron? You can pause the video and try the question again yourself and see what you end up with. So we are looking for, we are talking about the linear momentum. What's the order of the kinetic energy? We need to see a relationship between kinetic energy and momentum. Now, EK, kinetic energy, is given by a half times m times v squared. But momentum P is given by m times v. So I'm going to cook and see if I can get another m here. If I multiply by m, and divide by m. Now I have ek multiplying and dividing by m doesn't change anything, but it now gives me m squared v squared over m, 2m in fact, which is the same as momentum squared, because this is mv squared over 2m. And therefore, if we're going to look for the kinetic energy, it has to be, the electron has a linear momentum given there. So we are talking of a momentum of 4 times 10 to the power of negative 25. And we are squaring this and then dividing by twice the mass. The mass of an electron is 9.11 times 10 power minus 31 kilograms. We are looking for the order of magnitude, so we don't need to worry so much about exact values. So this is 16. 16 is close to 20, which is 10 to the power of 1. This is 16 times 10 power minus 50 divided by, this is 18 times 10 to the power of minus 31. We are talking orders of magnitude, so we don't really need to worry much about the exact values. So 16 is closer to 10 than it is to 100. So 10 power 1 times 10 power 50 divide by, this is also 10 power 1, closer to 10 power 1 in orders of magnitude, times 10 power minus 31. So this is 10 to the power of 51 minus, actually, what is that? Oh, and this is minus, that is minus, so minus there. So this is 10 power 49 minus 49 minus 49, and this is 10 power minus 30. And so if we take that up, we end up with 10 power negative 19. And so the closest answer for the kinetic energy in joules is 10 to the power of negative 19. Let's check if that is true according to the truth meter. So the answer is C, which is 10 power negative 19 joules. And that's the answer for that question. It required that you had a clue about what the mass of an electron was. In an exam, usually in the formula booklet, you have data values for some constants like the mass of an electron, of a proton, and so on. So that was probably an issue for some of you if you did not get to ask for that value. Right, next question. Question 7. A person with a weight of 600 newtons stands on a scale in an elevator. The image is shown. What is the acceleration of the elevator when the scale reads 900 newtons? So we do not know where this is going. From this diagram, maybe I draw another one next to it to help us reason out what's going on here. We are really just interested in the person. So a free body force diagram for this person is what we need. We can represent him with just a dot there. And he has a weight, he or she has a weight of 600 newtons. The scale reads 900, and as we discussed, the scale is the what we refer to as the normal reaction that is being exerted by the surface of the scale. So the reading there is 900. This is to suggest that the lift must be moving upwards because 900 is greater than 600, okay? And so the resultant unbalanced force out here, delta F, must be 900 minus 600, and this is what is equal to the mass times the acceleration by Newton's second law. So we are saying here that 300 must be equal to the mass of the person multiplied by the acceleration. Okay, what's the acceleration of the elevator? So the person has a weight of 600, so his mass, we can assume that that is, we divide by 10, so that is like 60 kilogram multiplied by A, and so A has to be 300 divided by 60. Would this be 5? We have an answer of 5. Doesn't look it. Okay, let's see if there is that option there. So 5 meters per second squared downwards. There is 5 meters per 1.5 meters per second downwards. And we know the acceleration is upward, so the downward answers are definitely wrong. The acceleration is upwards because we know that 900 is greater than 600. 1.5 meter per second squared upwards and 5 meter per second squared upwards, which looks like the most likely answer. But let's see. Yes, so the answer is 5 meters per second squared in an upward direction. Right, let's look at the next question. Yes, this is a question on collision. I believe I have a simulation to try and help explain this. We'll check it out. Two identical blocks, each of mass m and speed v, travel towards each other. So they have the same speed, they have the same mass, and they are traveling towards each other on a frictionless surface. The blocks undergo a head-on collision. What is definitely true immediately after the collision? What is it that is definitely true? The momentum of each block is 0, perhaps, but not necessarily true. The total momentum must be 0. Yes. Yeah, according to the law of conservation of momentum, the total momentum of the system before collision should be equal to the total momentum after the collision. So before the collision, this object is moving with a momentum of m times v in the positive direction. All right, but this is moving m times v in the opposite direction, so the two momenta before collision can cancel out, meaning the sum of the momentum before the collision is 0, so we expect that after the collision, the sum of the momentum should also be equal to 0. So the answer there is B. I have a simulation here. Let's see if it will work for us now. Sometimes it takes time. If it takes too long, we can move to something else. All right, so very quickly there. If we just click on this one, I have two objects here. I will make the masses the same. So if I increase that, let's say to 1 point, we can keep it as at 1, no big deal. 1. Can type there 1. We can type 1 there. And on this one we can also type 1. So the two objects have the same mass. I can also ensure that they have the same velocities. I will click values. So we are being shown the velocity of the first one as 0.5, and I can reduce the velocity of the other one also to 0.5. So if I do that, right, so they have the same velocity and the same mass. If I click them together, they collide and move back with the same speed. So if we look at the values there, we can tell it indicates that the momentum of the first one is 50 in the opposite direction. The momentum of the other one is 50 in the other direction. So because momentum is a vector quantity and they're in the opposite direction, the sum of the momentum is 0. So we are sure that the sum of the momentum of the two particles after they collide is going to be 0. Okay? All right. So the answer to that question was B. I can go back so you take a look. So the answer for this particular question was B. That's that we expect that the sum of the momentum must be 0. Okay. Question 9. A mass is released from the top of a smooth ramp of height h. After leaving the ramp, the mass slides on a rough horizontal surface. The mass comes to rest in a distance d. What is the coefficient of dynamic friction between the mass and the horizontal surface? One of the problems students face is where to begin with such a question. So this is an example of a question where kinematics would not work. The equations of motion don't work because the object is not moving with a constant velocity. It's not moving in a straight line, so we can't talk of a uniform acceleration. So in such a case, our best bet is to work with the idea of energy. So we reason that at this point, the object has got potential energy. So we could talk about how much potential energy it has here, and that would be, let me write it somewhere here, mgh. That is the potential energy. As the object comes down, when it gets to this point, all that energy, because the surface is smooth, all that energy becomes kinetic energy. So we could represent that by half mv squared. So it has got kinetic energy here, not that we need the kinetic energy, all right? And then that kinetic energy is reduced to 0 kinetic energy when the object gets to this point. Okay, so we can say that the energy that the particle has here has been, work is done by the rough surface to reduce that energy to 0. So we can say that the work done during this stage, work done, must be equal to the initial potential energy, which became kinetic energy of the particle. Since we are given height and not velocity, we don't need the formula in the kinetic energy form. We need the energy in potential energy form, EP, and therefore we can say here directly that mgh, the potential energy, which became kinetic energy, later became the work done, work was done against it so as to slow it down to stop. That energy effectively becomes heat and sound energy. So this is work done. The question is, what is the coefficient of dynamic friction between the surface? Now, this is the work done, but the work done is frictional force multiplied by distance moved against frictional force, which in this case is actually d. So that's the work done. So I can come here and say that FD, FSD is m times g times h. But frictional force, we learned that if the object is going to be moving here, then frictional force opposing motion is proportional to the normal reaction. So we can write this as mu times normal reaction, where mu is the coefficient of dynamic friction, and then we multiply by d must be equal to m times g times h. We continue. I will use this side, or maybe I can work with this space here. But R, which is the normal reaction, is equal to mg. So I can write that, maybe I can erase part of this. Not the best use of the space available, but let's see again. So this is mu times normal reaction, which is mg times d equals mgh. And so mu, mg and mg can cancel. and mu is simply h divided by d. All right, so to repeat that again, the object starts with potential energy at that height. As it comes down over that smooth ramp, the potential energy becomes kinetic energy at the bottom, and then the object is slowed down along the rough surface. So work is done against friction to reduce that energy to zero. The work done becomes the heat losses due to friction. Sometimes sound is also given. The result is, when we write this down, we end up with the coefficient of dynamic friction being h divided by d. Let's see what answers we have. GD over h, d over 2gh, d over h, and h over d. And so the answer is h over d. That's question 9. We move to question number 10. Question 10. Question 10 says, a sample of oxygen gas. So we have clearly moved on from mechanics. A sample of oxygen gas with a volume of 3 meters cubed is at a temperature of 100 degrees Celsius. The gas is heated so that it expands at a constant pressure. So pressure is kept constant. You're thinking about the 3 gas laws, to a final volume of 6.0 meters cubed. What is the final temperature of the gas? So if pressure is being held constant, then this has to be volume versus temperature, which I hope you will remember is Charles' law. So pressure is constant. So if P, pressure, is constant, then we are thinking Charles' law, right? Which says V1 over T1 must be V2 over T2. Please remember this temperature is in Kelvin, which some of you forgot. So the initial volume V1 is given to us as 3, and we are given T1 as 100, but we have to add 273 to change it into Kelvin, because these temperatures are absolute temperatures. So this is 373. The final volume V2 is going to be 6.0, 3.0. The reason why we put 0.0 is so that you know that these are to 2 significant figures. So your answer has to be to 2 significant figures. We are looking for T2. Okay, what's the final temperature? Substitute your values here, or first of all make T2 subject of the formula. T2 is V2 times T1 over V1. This equals V2 is 60 multiplied by T1 is 373. Everything divided by V1, which is 3.0. So it looks like 2 times that, which is 614 carry 1, 7 that Kelvin. This is temperature in Kelvin. I don't know if the answer is required in Kelvin or in Celsius, but if it is in Kelvin, that's it. If it is in Celsius, then theta has to be 746 minus 273. Some guys forgot to do this. So this is 3 there, 14 is 7, 6 minus 2 is 400, and that degrees Celsius. So the final temperature of the liquid, the oxygen, is expected to be 473. I hope that subtraction is right, but let's see. So option A is 750, option B is 470, option C is 370, and option D is 200, so the closest answer there is 473. Why am I getting 73 anyway? So anyway, that must be it. Hoping I didn't make any mistakes. Yeah. And so the answer is B. This was the closest answer there. So that was Charles' law. Please remember there is Boyle's law and there is also pressure law or Gay-Lussac's law. Can be looking at question 11 there as I erase this. Question 11, a bicycle of mass m comes to rest from a speed v using the back brake. The brake has a specific heat capacity, so we are in topic 3 now, a specific heat capacity C and a mass m. Half of the kinetic energy is absorbed by the brake. What is the change in temperature of the brakes? So temperature is going to change. We expect that the energy that you put in, is going to be m times c times delta t, where delta t is the change in temperature. But this energy is coming from the kinetic energy of the object, and only half of it. So we can say half of the kinetic energy, which is half m, I think it is capital M. Mass of the bicycle is capital M v squared, where v is the velocity of the bicycle. Yes, the initial velocity of the bike must be mass of the brake, which is small letter m, c times delta t. So the change in temperature, delta t, has to be equal to m v squared, where v is the velocity, over 4 small letter m c. I hope we have that option there. Let's see if that option exists. mv squared over 4 m times c. This doesn't look right or neat. M times c, where c is the specific heat capacity of the brake material. So mv squared over 4mc, mv squared over 2mc, mv squared over 4m capital MC now, and mv squared over 2 capital MC. Remember, small letter m is the mass of the brake, capital M is the mass of the bicycle, and the answer should be A. Next question, question 12. A mass m of water is at a temperature of 290 Kelvin. The specific heat capacity of the water is C. Ice at its melting point is added to the water to reduce the water temperature to the freezing point. The specific latent heat of fusion for ice is L. What is the minimum mass of ice that is required? Okay, so the key thing to remember here, ice is at its melting point. So ice is already at 0 degrees Celsius, right? So as usual, I prefer to draw that line. We have ice at 0 degrees Celsius, 0 degrees Celsius, 0 degrees Celsius, and we have water, which is at 290. So 0 degrees Celsius is 273 K, Water is at 290 K. That's about 17, I think, 17 degrees Celsius. 290 is 27 degrees Celsius. Okay, so this is water. And the water has a mass m. Mass is m. All right, so as soon as we put this here, the water temperature drops until it is the temperature of ice. Okay, the ice temperature does not change. Instead, it is the water whose temperature changes. Yeah, so the specific heat capacity of water is that ice is at melting point. So the ice will be turning into water. So in this case, we will have the solid turning into liquid, so m times L. In this case, we'll have water temperature changing to 0, so here we'll have m times C delta T. So how much mass of, so we can say this is mass of, this has to be the mass of water, and we will say this is the mass of the ice. Maybe we use capital L, capital M, and therefore heat lost by the water must be the same as the heat gained by the ice so as to melt. So we can say m times L must be equal to small letter m times C delta T. And so capital M, the question is, what is the minimum mass of the ice that is required? So that's capital M must be small letter m times C times delta T over the specific latent heat. That has to be the mass of the ice that is required. I hope I'm right. Let's see. That was 290. Delta T is given, so we can actually find the value of delta T. From here, delta T is going to be 290. 290 minus 273. That is, like I said, 17. So this is 17. So this thing is 17. So M is 17 MC over L. And I think that should be the answer. A there, B is there, C and D. And the correct answer should be A. Okay. So here we are reasoning that you have ice solid, the temperature is going to remain the same. So we have ice solid turning into water at 0 degrees Celsius. So latent heat only, no temperature change is occurring, so that must be the heat involved. In this case, the temperature of the water is dropping from 290 to 273, so a change in temperature means heat capacity. Okay, and the heat that is lost by the water must be the heat gained by the ice to turn into water at 0 degrees Celsius. So we equate these two as we have done before. So this is the case of mixtures. The left hand works faster. Right, that was question 12. Question 13. Question 13. Energy is transferred to water in a flask at a rate P. So rate P there is power, energy per second. The water reaches boiling point and then P is increased. So when the water reaches boiling point, the power is increased. So more energy is now being supplied per second. What are the changes to the temperature of the water and to the rate of vaporization or evaporation of the water after this change? Well, the water has reached its boiling point, so while the water is boiling, the temperature is bound to remain unchanged. So the answer here can only be B or C. A and B are taken out by this that fact discussion about increase in temperature. So while water is boiling, the temperature will not change even if you increase the rate of heat supply. Okay, so that will continue until all the water has evaporated before the temperature starts rising again. Now the rate of evaporation is going to increase because you are supplying energy and the molecules need the energy in order to evaporate. So the more energy you supply, the more molecules that are able to break bonds and escape from the surface of the liquid. And therefore the answer to this question has to be D. Question 14. Boiling water is heated in a 2 kilowatt electric kettle. So the power is given there very quickly. Power has been given to us as 2000 watts, right, in SI unit. The initial mass of the water is 0.4 kilograms. So mass of the water is 0.4 kilogram. Assuming the specific latent heat of vaporization of water to be 2 megajoules per kilogram, so specific latent heat of vaporization is 2 times 10 power 6 joules per kilogram, right? What is the time taken for the water to vaporize? Well, energy supplied must be equal to M times L, all right? But the energy supplied is power times time. So this must be the mass times the specific latent heat. We are looking for the time taken, so T has to be mass times L divided by P. The mass is known, 0.4 times the specific latent heat, 2 times 10 power 6, everything divided by the power, which is 2 times 10 to the power of 3. Our answer is going to be the 2 and that cancel, 10 power 3 and that is 10 power 3, so this should be about 400 seconds. 400 seconds, which we can change into minutes if that was required. But let's see, 250 seconds, 400 seconds, 2,500 seconds, and 4,000 seconds. We expect the answer to be 400 seconds. You can always pause the video or rewind and check again to see that you've understood what we've done. You will notice that the formulas only come easily if you are practicing. Otherwise, you spend too much time thinking about which formula is relevant to what question. So this is the reason why I urge you to keep practicing. Solve as many questions as possible, and when you can't find any, see me so that we can find you questions. All right. Question 15. Is that the question we just answered? Yes. Oh, question 15 is here. Is that it? Boiling water is heated what is the time taken for all the water to vaporize? So we did that. I think there is part of the question coming up. Did we finish it? So okay, I think I have the wrong question here. This question was asking for which graph was showing the right relationship. This was BA. Yes, this was a question about boiling water heated. The initial mass of water is that's not the question. So we will skip this question. Either way, when you check your paper, the answer to this question, I think, was the answer was C for this particular question. I think I forgot to, I didn't write down the exact question. Question 14 has been carried forward, so I didn't write it down. The answer was C, which is this graph here. We can look at this in class tomorrow. Question 16 now is theory section, structured section. A sample of vegetable oil initially in a liquid state is placed in a freezer that transfers thermal energy from the sample at a constant rate. Constant rate means power, energy being taken out per second, that is power. The graph shows how the temperature T of the sample varies with time. So we start with a temperature of 290 there. The temperature drops steadily to 250. So perhaps that's what we want to remember. So after 30 seconds, the temperature drops from 290 to 250. So that is a drop of 40 degrees Celsius, which I want you to remember. After that, the temperature will remain constant, but remember, heat is still being taken out of the vegetable oil. So we can assume that this is the point where the oil changes from solid state, from liquid state to solid state. Yeah. Let's look at the question. The following data is available. So in blue, you will see the data that was given in the question. I have repeated the graph there. The first part of the question says to calculate the thermal energy transferred from the sample during the first 30 minutes, and I have already done this calculation. The rate, which is really power, energy being drawn per second, is 15 watts or 15 joules per second. All right. Therefore, in 30 minutes, we are being asked to calculate the thermal energy transferred from the sample during the first 30 seconds. Now, the heat is being supplied at a constant rate of 15 watts or 15 joules per second. So in 30 minutes, if every second we are taking away 15 joules, how many joules do we take out in 30 minutes? We have to take the 15 joules for every second, and then we have to change 30 minutes to seconds, which is 1800. So it's going to be 15 times 1800, which gives us 27,000 joules. So this was relatively straightforward. Some guys didn't get it, of course. Part B of the question says estimate the specific heat capacity of the oil in its liquid phase. What is the specific heat capacity? Well, temperature has changed from 290 to 250, so we can say energy that has been drawn out is M times C, mass times specific heat capacity, multiplied by the change in temperature there. So if you make C the subject of the formula, we have Q over M multiplied by T2 minus T1, which is delta T. The amount of heat being given during that 30 seconds when the temperature is changing from 290 to that. The energy we already calculated to be 227,000. The mass of the oil from up here, the mass of the oil is 0.32, and the temperature change is 40. When you plug that into your calculator, you will get 2100 joules per kilogram per Kelvin as the specific heat capacity of the oil. Next question was that? We just did that already. Next part C. The sample begins to freeze during the thermal energy transfer. So freezing during the thermal energy transfer. So at this point here, the sample is freezing. Along the plateau, the sample is freezing. The question is for you to explain in terms of molecular model. So this is a very important sentence here. In terms of molecular model. So there are two ways we can explain these, the behavior of the oil. If you're told to just explain what happens during that time, we can explain it microscopically or macroscopically. So if it's explaining macroscopically, that is in bulk substance amount, then we are talking about things like the volume of the oil, right? The temperature of the oil, like that. If we are to explain it microscopically, then we must go in and talk about what's actually happening to the molecules themselves. So in terms of molecular model, our statements must include things that are happening to molecules, and we must be mentioning molecules. So we must mention molecules, we must mention things with intermolecular forces or bonds, we must talk about kinetic energies of individual molecules, we must talk about potential energies of individual molecules. And so the answers that I've put here are talking about that. Giving any three of them would score you the 3 marks that was required. So the first one there says the intermolecular bonds are formed during the freezing process. So you're talking about bonds, okay? Bond forming process releases energy. So when you take out energy from a system, you allow the molecules to come closer together. That means more bonds are produced, right? The molecules stick together. The second explanation there that you could also have given, intermolecular potential energy decreases. Of course, if you're taking away energy, the potential energy of the molecules decrease. The result is that the molecules come closer together. Remember, when you give molecules potential energy, it's the energy of separation, so the molecules move apart. So if you take out that energy, then the molecules tend to come closer together. So talk about what is happening in terms of the potential energy of the individual molecules. The other thing you can talk about is talking about the average kinetic energy of the molecules, which does not change. So during this process, during this plateau process, the kinetic energy of the molecules do not change whatsoever. You can, of course, also talk about the fact that the temperature is related to the kinetic energy, and since the temperature remains constant there, then the kinetic energy of the molecules must also remain constant. So your discussion must involve talking about the kinetic energy of the molecules, random kinetic energies. You must be talking about potential energies of the molecules. You must be talking about the bonds, forces holding the molecules together. You can also be talking about the separation between the molecules. So any of those things, and talking about them in relation to the molecules as opposed to the bulk matter would be the correct way to handle this question, okay? All right. Next was D, calculate the mass of the oil that remains unfrozen after 60 minutes. So how much is left unfrozen? Okay, so after 60 minutes, you have supplied energy equivalent to, unfrozen, meaning we are now here, so it's going to be the next 30 minutes when the oil is freezing. So during freezing process, the amount of energy used in 30 seconds, remember we are still supplying at 15 watts or 15 joules per second. So in 30 seconds, during this plateau, 30 seconds, we have supplied the same amount of energy, which is 27,000, all right? And so from the specific latent heat, knowing that latent heat is mass times specific latent heat, the heat taken out, L, capital L is m times small letter l, so we can find the mass that has been frozen. So the mass that freezes is L over capital L over small letter l, which gives us 0.21. So some people solved this and stopped here, where this calculation tells us what has been frozen. But the question is asking us what remains unfrozen. So we have to take the original mass, which was 0.32, subtract the amount that has been frozen, and what is left, this is the mass that is still unfrozen. Yeah? Right, question 17. The graph shows the variation with time t of the horizontal force F exerted on a tennis ball by a racket. The tennis ball was stationary at the instant when it was hit, right? The mass of the tennis ball is 5.8 times 10 power third. The area under the curve is 0.84 Newton seconds, okay? So what is the question? Keep that in the graph in mind, but I think I have put it again. So the question is, before we go to the question, one of the things you must always remember, this is a force versus time graph. In an F versus T graph, the area under the graph is always the impulse, and even if you couldn't remember that, as soon as you see the unit being given for the area under the graph, Newton seconds, that is the unit of impulse. Okay, so the area under an FT graph refers to the impulse on the object, the impulse in this case on the tennis ball. Okay, that's key concept number one that we want to remember. Key concept number two is, of course, Newton's second law of motion. Newton's second law, in the way that we normally remember it, is to say force equals ma, which is not necessarily true. It is, in fact, force equals to the rate of change of momentum, which we write as rate of change of mv. Okay, that's momentum. If we differentiate this, we get, that's product rule, we get m dv by dt plus v dm by dt. Okay, so dv by dt is what we know as acceleration. dm by dt is the rate of change of mass. So if an object is moving such that its mass is also changing, then Newton's second law in full looks like this. All right, so we use the Newton's law in this form. This is just a reminder. We use it in this form only in cases where the mass of the object remains stationary, so that dm by dt is 0. Okay, so keeping that in mind, this is a tennis ball, and we know that its mass remains the same, so we can get rid of this part of Newton's second law, and we have that. This is what ma is, right? This is F is equal to m dv by dt. We could write this, we could rearrange this. If we make, we can cross multiply F and T, and we can write this as F delta T, that's this delta T, is m delta V. And we say impulse, the left-hand side there, is called impulse, equals the change in momentum, because this is v minus mu. So v minus u is the delta V that we have there, is change in momentum. So this is another way of stating Newton's second. So the first way is to say the force acting on a body is always equal to the rate of change of its momentum, like that. Or we can say the impulse on a body is equal to the change in its momentum. Is another way of making the same statement. So now we know from here that this impulse here is the area under the graph, which is 0.84. Okay, but let's now look at the question. Yeah, so what question are we being asked here? We are given the area under the graph, and we are given the mass, and we know that the initial velocity is 0 because it says variation of time, the tennis ball was hit from, did I leave it behind? Yeah, was stationary. So the tennis ball, says here, the tennis ball was stationary at the instant it was hit. So the initial velocity of the tennis ball was actually 0. Now we can move on with that information in mind. Calculate the speed of the ball as it leaves the racket. So the tennis ball is accelerated. We accelerate it from a speed of 0 to some final velocity. Okay, so during this time when the velocity is changing from 0 to this, the ball is being accelerated. There is a force that is acting on it. And we are saying that the force acting on the ball at this time is the rate of change of momentum. So it is m delta V over delta T. Okay, We are being asked for the final velocity. I can write this in a way that we understand. So we can say F equals ma, which is mv minus u over t, and therefore F times t, this times this, must be mv minus u. Okay, F times t, we know it's the area under the graph, which is 0.84. Okay, this must be equal to mass of the ball, which was, I think, 5.8 times 10 power 2. I'll try to confirm that. V is unknown, but U is 0. And when you make V the subject of the formula there and look for it, we should be able to get the answer. I think I've done it. Let's just see if I've done that calculation. So remembering this material, I've already talked about this. These are values given. So here's my calculation of the same thing here. I typed it so that I don't have to keep writing on the screen all the time. So impulse is change in momentum is F times delta t there. So 0 points, so keep that in mind. Impulse is area under the graph, which is 0.84, must be equal to mass times change in velocity. I already wrote that down. If you make V the subject of the formula, you get area over that mass, and the answer here is 14.5 meters per second. So that must be the velocity, the maximum velocity reached by the ball, okay, as it leaves the racket. The next part is show that the average force exerted on the ball by the racket is about 50 newtons. So force exerted on the force that the ball exerts on the racket is the same as the force that the racket exerts on the ball. Keeping that information in mind, again, impulse is area under the graph, which is force times change in time. We know the time for which contact is made. So the time, we can get that time by coming here and we say, okay, from about 13 there up to around 27. So I say 27 minus 13 is the time for which this is happening, right? So the time there multiplied by, don't forget, it's multiplied by 10 power minus 3 because the time here is in milliseconds. So some people forgot to do that, and if you do that calculation, you get 53 newtons, which is approximately 50 newtons. Part C, determine with reference to the work done by the average force the horizontal distance traveled by the ball while it was in contact with the racket. What is the horizontal distance? Work done is related to, work done is force multiplied by distance, right? And therefore, keeping that information in mind again, work done is force times distance. Work done is also the kinetic energy that is given to the ball. So if we know the speed that it gains, we can find the kinetic energy that it gathers. This is going to be the kinetic energy. We know the speed, I think it was 14.5 we got for this. So we know the kinetic energy we've given to the ball. If we know the kinetic energy, that must be related to the work we've done to do that. So the distance covered multiplied by the force applied is the work done. The question is for us to find, with reference to the work done by the average force, determine the horizontal distance traveled. So we are looking for delta S there. So delta S is mv over 2f based on the equation there. If we substitute in, mass is 5.8 times 10 power minus 2. The velocity is 14.5, so we square that. In the denominator, 2f, we found f to be 53, okay, in the previous case. So if we calculate that, we get the distance traveled to be 0.12 meters. Question 17. Draw a graph to show the variation with t of the horizontal speed of the ball while it was in contact with the racket. Numbers are not required in the axis. So what we know is that as the ball sinks into the racket, so first of all it sinks in. The racket behaves like a trampoline. So it sinks in. As the racket comes in, the ball kind of stays. So the acceleration is slow. So starting from 0, it accelerates and then accelerates so that the acceleration is high up to a certain amount, and then as it leaves, the racket, the acceleration reduces because the force of contact becomes less. So we expect this graph to look something like this, an increasing then decreasing gradient. Do I have this? Yes. So an increasing then decreasing gradient. So initially a small amount of force is acting, and that force, so this is showing a very large rate of change of a very large acceleration. So this is where the force is maximum, and then as the ball, the contact between the ball and the racket disappears, that force becomes less. The rate of acceleration becomes less, and the ball now moves at the velocity attained. And this velocity here was 14.5 meters per second. Question 18, and then leaves us with one more question to go. This is a very important question. This relates to your IAs and to question 1 in paper 3. It's going to be a long question, usually 20 marks or more. So this is a serious question. This relates to the IA that goes to the IB for marking, so I will only be happy when everyone is absolutely able to answer this question. Okay? So a spherical soap bubble is made of a thin film of soapy water. The bubble has an internal air pressure, PI, and is formed in air of constant pressure, P naught. So think of a bubble, okay? That is a bubble there. Inside there is pressure there, and on the outside we have pressure PO. So this is the pressure inside, pushing the bubble from the inside, like that, PI. And on the outside, we have atmospheric pressure pushing inwards like this. Okay, so P out. So there is a net pressure, delta P, which is PI minus P naught. Okay, this is what we are talking about. Now we are being told that I don't want to write PI and P naught, so I'll write delta P, the change in pressure. I'm writing in the wrong place there, sorry. So I can say that the change in pressure, delta P, must be equal to 4 rho over, over R, where R is the radius of the bubble. Okay? So this is the relationship. Okay? The theoretical prediction for this variation is given by that. So that is this formula here. It's a theoretical prediction where gamma is a constant for the thin film and R is the radius of the bubble. Data for the pressure difference, delta P, and R were collected under controlled condition, that means in the lab, and plotted as a graph showing the variation of changes in pressure. So change in P going to the y-axis is change in P, and in the x-axis I think there was an R, right? Okay. With 1 over R, not just R, 1 over R, which makes sense from here. Let's just go to the question. Right. Yes, so this is the first part of the question. What question are we being asked? Suggest whether the data are consistent with the theoretical prediction. So the theoretical prediction is that that pi, so that pi minus p naught, so delta p and that are proportional. If you look at this, this suggests this is the equivalent. So we have, you have pi minus p naught equals 4 gamma times 1 over r. This is the equivalent of y is mx plus c, whereas this is plus 0, so the y-intercept is 0 there. So we expect this graph to cross the y-intercept. This is going to be our gradient, okay? Because if this is a graph of y and this is x, makes sense that this is pi minus p naught and this is 1 over r. So you can see that there is that semblance. And because of that, if we look at the graph, does the graph give this suggest that this should be, if we draw a graph of this and this, we should be able to get a straight line. And when we look at the graph, you can see that we end up with a straight line. So to answer the question, suggest whether the data are consistent with the theoretical prediction. The answer to this is, of course, yes. This is consistent with the prediction because we end up with a straight line that passes between all the error bars, in fact passes between through all the points. We cannot talk about the line passing through the origin because you can see this data here starts from 10 and not 0. So of course we expect that that will go and meet 0 there. So you cannot say it's not passing through the origin because that is not showing, okay? So the correct answer to say here is yes. The data, we end up with a straight line and it's passing between all the error bars. So this is pretty good linear relationship. That the data is consistent with the theory. Okay, so yes, the first mark is for saying that yes, it is consistent, and then you say the straight line of best fit suggests that the difference in pressure is proportional to the reciprocal of the radius. Okay. The second part of the question says to show that the value of gamma is about 0.03. Now, looking at what I had written here, we had said that the gradient is 4 gamma. There, I've just erased it again. The gradient is the same as 4 gamma. Yeah, so we're saying, I think I've put the solutions here. Maybe I just go ahead and see if I can add something on it. So the gradient was equal to 4 gamma because 4 gamma was the coefficient of 1 over r. So therefore that must be the gradient. So our job is to go and look for the gradient of the line and equate to 4 gamma. Okay, so we need 2 points selected from the line or plotted points if and only if they are on the line. So we need 2 points that we're going to use to look for the gradient. The point here is that the 2 points that we select must be on the line of best fit. If the plotted points are on the line of best fit, then we could select we could choose from the plotted point. But if a plotted point is not on the line of best fit, then we cannot choose it. Okay, this is another thing that I've talked about again and again, but some people don't seem to get it. So if we select from the line of best fit, let's see if I have it somewhere. Did I do this? We get the value of m to be 0.1, and so the value of gamma becomes 0.1 over 4, which is 0.1 0.025, which is approximately 0.03. That is what you get. Identify the fundamental unit of gamma. I could go back. I need to talk about this first. So what I was saying here is to find the gradient, we need to pick 2 points. The 2 points we pick must be on the line. We can only pick these points here, can only pick these indicated points if they are on the line of best fit. That's point number 1. Point number 2 is that the points that we choose must be as far apart as possible. So I would suggest that you extend this line to cross the y-axis so that you have as large a distance between the 2 points as possible. In fact, the mark scheme for this, the IB mark scheme for this question suggests that if this distance here is less than, 2? There's a certain value that if it's less than that, then they would deduct marks from you. So for me, I just suggest take the very, very far ends of the line, and the points you pick must be on the line of best fit. Okay. Now let's go back where we were. The gradient is that we calculated the value of lambda to be 0.025, which is approximately 0.03. Okay, identify the fundamental units. To identify the fundamental units of gamma, those must be the units of the gradient. So if you look at the graph there, the units of this is pressure, and this is 1 over r. So in fact, the unit for the gradient, so gradient is found by the unit of pressure, which is Pascal, over the unit of 1 over radius, which is per meter. Okay, the Pascal was the kilogram force, kilogram meter per second squared, which is force, over area, which is meter squared, and then meter square per meter down. This one here now is here. Okay, so this is force over area, which is pressure, and if we simplify this, we get kilogram there. Yeah, kilogram there. Where is this goes with one of this, and this will cancel because this is up. This is meter up here. With this is meter squared, which cancels with this. So this 3 will cancel, and we are left with kilogram second squared. That should be the unit of gamma. Okay, so just look at it. You should see that that is kilogram second squared for the unit of gamma. And now we can go and see it. So to find the unit of gamma, gamma is proportional to the gradient, because 4 times gamma is the gradient. 4 has no unit. I'm saying 4 gamma was the gradient. 4 has no unit, so the unit of gradient is the same as the unit of gamma. So to find the unit of gradient, we go back to the graph, and we see that it is the unit of pressure over the unit of 1 over r, which is per meter, like that. Right, so that's how we find the unit of the gradient, and therefore the unit of gamma. I believe I've done that calculation. The unit of gamma, since gamma is that, the unit of gamma is the unit of pressure times the unit of radius. Yes, like that. So that gives us unit of pressure. This is pressure here, force over area, times radius there. Force is kilogram meter per second squared. Area is meter squared multiplied by m. So you can see this m and that m multiply, and we have m squared, which cancels with the lower m squared, and we are left with kilogram per second squared. What did I get? I thought I got kilogram second. It should have been per second squared, per second squared. Yeah, yes. Yeah, that makes sense. That is correct. Because Pi minus P naught was equal to 4 gamma over R. So move R to this side. You have, you ignore the 4, doesn't take part in unit calculation. So gamma is given by pressure times R. So the unit of gamma must be the unit of pressure multiplied by the unit of radius. And like that, we get that. Okay. Question 18. D, in order to find the uncertainty for gamma, a maximum gradient line would be drawn. On the graph, sketch the maximum gradient line for the data. So here is the line. We want to draw the maximum gradient line. So to draw the maximum gradient line, we only need 2 points. We go to the far end point, so we go for that point there, and we go for this point here. For this point, we pick the lowest point there, okay? We pick the lowest point here, there, and on this side, we go to the higher point on the error bar, right? Should be this one there, okay? And then we join that with a straight line, and that is the line of maximum gradient, okay? And that was 1 mark. You needed to do that. Now, the percentage uncertainty for gamma is 15%. State gamma with its absolute uncertainty. Absolute uncertainty is delta gamma. So, percentage uncertainty is given by delta gamma over gamma. Percentage uncertainty is delta gamma over gamma times 100%. And this is 15. So the question is, what is absolute uncertainty, which is this one here? So the absolute uncertainty in gamma has to be 15 times gamma over 100. And that is 15, and gamma was 0.03 or 0.025, whichever one you like, you can use, no problem. And this becomes what? If we do this calculation, so that's this what I've written down here. Let's just remove this. Yeah, gives us 0.0045. So this gives you the first mark, and then you have to reduce that to one significant figure because your previous value, because this is to one significant figure here, so your answer has to be to one significant figure. It was okay if you wrote 0.04, that was fine. If you wrote 0.05 by rounding that up, by rounding the 4 up because of the 5 there, and you wrote 0.05, that was also fine. Okay, so it's that, or you can give that and there's no problem, both answers are valid. All right, next, the expected value of gamma is 0.027. This is a very, very important area now. It's about evaluation when it comes to writing your IA. This is the bit where you have found your answers. You are now comparing with the literature value. So this is the equivalent. This is what you'd refer to as the literature value, the true value. Okay, you've worked out your value, which we found is 0.03 or 0.025, and this is the literature value. Comment on your results. So in this case, we are comparing our answer with the literature value, so we must be thinking about the accuracy of the result. Accuracy is when you compare your data value with some literature value. How far away are you from the literature value? So to do that, I have actually discussed both cases, because the other thing we want to discuss also is the precision, all right? Which is related to to random errors. Huh? How close together are our data values? How close together are our results? Where do our answers lie? So this is what I've done. I've discussed 2 cases, right? First, I want to compare what my answers are. Let's see. So I look for, this is what I would expect you to do as my student. If you are going to evaluate your result, the first thing you want to do is to check the random error, how random errors have affected your results. So basically you're looking at how precise your results are. To do so, you want to draw the line of maximum gradient, the line of minimum gradient. So you look for the maximum possible value of gamma and the minimum possible value of gamma. So to find, this is the line I've drawn there is to help us find the maximum possible value of gamma. Notice that I've drawn the line to extend to the y-axis. Okay, I've extrapolated it, and also to cross the other end there at 25. The line x is 25, or if you like, r power negative 1 is 25. So we want it to cross all through, so that when we pick the points, we also pick the points at the end, right? So I need this point here. I need to find its coordinates. So the coordinates of that point are needed. I also need the coordinates of this point here. Okay, so the coordinates of this point is 10, which is the x coordinate there. The y coordinate, I looked at it and it's about 0.90. I also need the coordinates of this end, which is 25 for x, and 2.6, if you check carefully here, 2.6 is pascals is the value of y there. So to find the gradient of that line, of course, change in y over change in x, which gives me the maximum possible value of the gradient, 0.1133, and I think it was 3 recurring. Okay, to get the value of gamma, I have to divide this by 4, because 4 gamma equals to the gradient. So if I divide by 4, I get 0.028. So my maximum possible gradient is 0.028. I also need my minimum possible gradient. So again, I draw a line of minimum gradient, which must pass through the highest point here and the lowest point there. Okay, I need the coordinates of this point, and the coordinates of the other point. The coordinates of the first point is 10 and 1.10. The coordinates of this end is 25 and 2.4. And again, I can look for the gradient of the line of the minimum line. The gradient is 0.0867. And when I divide that by 4 to get the minimum possible value of gamma, I get 0.022. What we notice then is that our value of gamma, which 0.03, we found it earlier, the gradient of this white line, gamma from the white line, 0.025 or 0.3. Okay, so that value lies between 0.022 there and 0.028. So I have put that there. So our experimental value lies between a minimum possible value of 0.022 and a maximum possible value of 0.028. Okay, we can use this to describe the spread of our data value, how much random error there is. Okay, so how much random error is there? To do that, we find the absolute uncertainty here by taking the highest value, subtracting the lowest value, and dividing by 2. And then we can take that and divide by 0.025 and work out that as a percentage, and that will tell me the percentage spread. Okay, so here is my calculation. So to work out the precision, which means how close my data values are together, reliability in terms of each other, is called precision, and it's a measure of the random uncertainty in the measurement. I'm going to use this result here, which is the uncertainty in gamma in terms of random uncertainty is maximum minus minimum divided by 2, which is 0.003. And if I can use, so now I'm representing gamma in terms of my experimental value and uncertainty, or the spread there. I can work it out as a percentage, which gives me 12%. So once I get my 12%, I can now make a statement of reflection, right, or evaluation. Maybe 12% is a very, very large number to be away from, the expected value. So we would say my experiment suffered from a lot of random uncertainties. If I think that 12 is too big, and indeed 12 can be very big. However, there is no correct answer. You can say 12% is relatively small in terms of this experiment, and therefore this, in terms of random uncertainties, there was very little of it, and this experiment was successful in that sense, okay? So there is really no incorrect answer. So discussing precision, our mean experimental result of 0.025 falls within the range of plus minus 12%. Okay, so then you decide whether you want to say that this is good enough or this is not good enough on the basis of the experiment that you are carrying out. So if this was an experiment that was difficult to do, you had to carry out an experiment for 6 hours, 12% is very, very good. But if this is an experiment that you carried out with some sophisticated measuring device like data logger, and you're getting 12%, then 12% can be too big, all right? So the statement that you give once you've ended up with this calculation will be based on the kind of experiment you are carrying out. But in general, no answer is wrong. All you have to do is explain, 12% on the basis of the experiment that we carried out. 12% is not a very, very large uncertainty, and therefore I can say this experiment was successful. Okay, so this is an evaluation or data analysis that goes towards discussing the precision. How precise were my measurements? How close together? How reliable in terms of each measurement was my data? And this is what you get. The other consideration is comparing our results. So precision is about comparing my results with one another. All the results put together, you compare them, okay? That is about precision. The next thing is a discussion of accuracy. Accuracy is comparing your result with some standard result, like some literature value, right? You've measured the speed of light using your equipment, then you compare with the standard known speed of light. You've measured the speed of sound in air, and you compare with some known speed of sound. So that would be a discussion of accuracy. How accurate are you in comparison with some known standard value? Okay, so this is what I want to discuss now. Okay, so accuracy is about what happens to the system, how systematic error may have affected our results, right? So to do so, we need to take the literature value. We are told that it was expected that the value of gamma was 0.027. Our value was 0.025, okay? So Y lit means the literature value for gamma. Y experimental is the value that we got by carrying out the experiment. So we want to see how far our experimental value deviates from the literature value. So we will take the literature value, subtract our experimental value, and everything divide by the standard literature value. Whatever we get will tell us how accurate we are. So our gamma there, if we substitute in the values, I get 7.4%. So 7.4 systematic uncertainty, again, that's quite nice. I mean, definitely lower than 12. Usually 7.4 is also a big number. So uncertainties that will generally be acceptable are 2-3% are good. But again, there is no, in the IB system, there is no correct answer. If you say, you can say 7% is too much and explain why it's too much in terms of the experiment that you did. Or you can say it is too little and therefore the experiment was successful. We are very close. I mean, we are only 7.4% away from the data. And given the difficulties that I faced during carrying out of the experiment and so on, the uncertainty, the systematic uncertainty is small enough. And from this, we can conclude that the experiment was successful. So this discussion of analysis, this is analysis and evaluation of our result, is something that we really have not done in great depth, but which is going to carry a lot of marks in the IA. So if you can get hold of this and make use of it as we progress, there is an IA coming up which will require you to use this idea. I want you to make, yeah. One moment. Right, that leaves us with, I believe, how far are we from the end? Okay, so then again we can discuss our results, saying there that our experimental results, 0.25, yes, deviates from the true value or the literature value by 7.4%. So again, it's for you to decide whether 7.4 is good enough or it is too large. Okay, now we go to the last question, which was question 19. A student investigates how the period t of a simple pendulum varies with the maximum speed v of the pendulum bob by releasing the pendulum from rest, okay, from different initial angles. So if you release it from a small angle, the maximum speed is small. The bigger the angle of release, okay, as it swings like that, the bigger the angle, the higher the speed will be when it reaches the bottom of the swing, okay, like that. So by changing the angle, you can change the speed and therefore the period of oscillation, okay. Here is the graph showing how the period changes with the velocity. And the first question is, suggest, and I've underlined it there, by reference to the graph. So your suggestion, your explanation must be talking about what you see on the graph. So suggest by reference to the graph why it is unlikely that the relationship between t and v is linear. So one of the things you could say is, if we drew a straight line on the graph, there's no way that that straight line can pass between all the error bars there and pass through the origin. So there is no straight line drawn through the points that will pass between all the error bars. Because of that, this relationship is not linear. You can also say that the line of best fit drawn through the points appears to be a line with increasing gradient, okay, or a parabola or something like that, okay. So a straight line drawn through the points cannot pass between all the error bars, and that is a good indication that the relationship is not linear, okay. Here's my answer. A straight line drawn through the points cannot pass between all the error bars, and this is the reason why the relationship between t and v is not linear. Could also say a line of best fit through the points has an increasing gradient. Okay, those are all possible answers you can put there. So whatever you're doing has to do with what you're seeing about those points there. Okay. Determine the fractional uncertainty, one moment, determine the fractional uncertainty in V. So the fractional uncertainty in V when t is 2.115. Fractional uncertainty in V means delta V over V. Okay, so we are looking for delta V over V. Let me leave that out, I'll write it once we have the graph here. We want delta V over V when t is 2.115. So when t is 2.115, when t is 2.115, I think there, so 2.115 is somewhere there. That is 2.115. we want to know the value of V there. So the value of V down there, how much is it? It was 1.15. So we know the value of V. We are looking for delta V over V. That is the fractional uncertainty. Okay, so we already know what V is. We still need delta V. So to do that, we go and look at the error bar. So V is known. To find delta V, which is this here, we are looking at the horizontal error bar because this is V. So this is the lower value there. It ends somewhere, you see where the arrow is. Then I have the other side. So we have those two, and if you look at that, that distance between those two arrows is 0.1. Okay? But those are the ends of the error bar. And so the uncertainty there must be that distance divided by 2. So 0.1 divided by 2 would be 0.05. Because of that, delta V is 0.05. So to find the fractional uncertainty here, we have to say delta V divided by V, 0.05 divided by that, which is 0.04. It's as simple as that. Okay? Yeah, you would be allowed to say 4% if you didn't want to leave it like that. So that is the fractional uncertainty. 4% would be talking about percentage uncertainty, but in this case, even that would be allowed. Okay, 19C, the student hypothesizes that the relationship between T and V is T equals A plus B V squared, where A and B are constants. To verify the hypothesis, a graph showing the variation of T with V squared is plotted. The graph shows, so it is T versus V squared. So obviously you can see that that would be the equivalent of Y, and this is C, and this would be MX. So our X is V squared. Okay, so there is my line. So T in the y-axis versus V squared in the x-axis. We expect that our gradient is going to be B, and our y-intercept is going to be A. Is that simple? Okay. So the question down there, part A, is to determine B giving an appropriate unit for it. So determine B giving its appropriate unit. Okay? So we know that B has to be the gradient, right? So what is the gradient? To find the gradient, the first thing we want to do is to extend that line to go to the end. So we say we extrapolate. So extrapolate this to go across the y-axis, extrapolate this one here so that it goes to the end. So if we do that, okay, B is the gradient. So first we extrapolate the line to cross the x-axis, and the line V squared is 5. So this line here is line V squared is 5, or you can say line X is 5, okay, because this V squared is the x-axis. Okay, so we want to stretch that. So I've drawn that line there in yellow. I have extrapolated it to cross the ends. Then I need the coordinate of that point. I need the coordinate of this point here. I also need the coordinate of the top point there. Okay, so those are the coordinates, and I can make use of those to find the gradient. y2 minus y1 over x2 minus x1. So the gradient is 2.161 minus that over that, and I get a value for the gradient of 0.0126, which is approximately 0.013 to 2 significant figures. Okay, so that is the value of B. That gradient is the value of B. But we also want to find the unit. Well, the unit of the gradient is the y value divided by the x value. The y value is seconds, so the unit is going to be, I'll write it here. So second divided by the unit down there, the unit of v squared is meters squared per second squared. So this second squared goes up there, and we have second cubed over meter squared, which we can write as second cubed per meter squared, like that. And that is actually our result. Let's see. Okay. So the unit is time in the y-axis, the square of the velocity in the x-axis, so y divided by x, okay, and that is the unit of B. Part D of the question. The line of the minimum and maximum gradient are shown. Estimate the absolute uncertainty in the value of A. Remember, the value of A is the y-intercept. So we want to estimate the absolute uncertainty, delta A. So there are our two lines, okay? So if we're going to find this, of course, we need to have them extended so that they cross the y-axis. So we need to get those y-intercepts. We find the, so A is the y-intercept first of all. Let's remind ourselves of that. To get that, we need the coordinates of that point. That is the minimum possible intercept, okay? We also need the other coordinate point. So the minimum value is 2.094. That's C mean. C max is, if you read that carefully, I think it was 2.10. 101 is acceptable, 2.10 is also fine. So that was the maximum value of C. So to determine delta, so the value of C is the value of A. A is the y-intercept. So effectively we have A mean and A max. So to find the absolute uncertainty, subtract those two and divide by 2 as we did earlier. So we have that, subtract, and we get delta C is 0.03. This is the value, the absolute uncertainty in the value of A. Okay, I believe that's the end of the discussion. I hope if you look at this and you find there is some difficulty, let me know and we can go through it again. Whatever question you find is confusing, we can go through it again, right? Otherwise, see you later when we meet for the lesson. Thank you very much.